Okay, everybody, here is this second video, the so-called bonus material. We're going to talk a little bit about polarization and then scattering and absorption. Okay, so let me start off with talking about birefringent materials. These are cool materials, and they can do neat things with polarization states. So these materials exhibit two values of refractive index for a particular frequency of light. We mentioned when we talked about dispersion that a normal material will have slightly different index value for each frequency, which gives rise to the dispersion properties of the material. But these birefringent materials actually have two values of index for each frequency, and the values depend which value gets, quote, used or is characterizing the material's response. It depends on the orientation of the electric field of the light wave at that particular moment with the so-called optic axis of the material. So the electric field oriented one way, you use one index for the material. The electric field oriented another way, there's a different value of index. So a common material is calcite. And again, if you were a rock collector when you were young, you may have had a calcite crystal. So in any birefringent material, and birefringent, we're usually talking about solids. Liquids can also exhibit birefringence, although it's usually referred to as optical activity. Okay, so in this calcite, there is a definite axis. We call it the optic axis. And if the electric field is parallel to that axis, there is one value of index. If the electric field is perpendicular to that axis, then the other value of index is the one that's important. And this birefringence arises because of, in a crystalline solid, the orientation of the atoms in the so-called crystal lattice is why you have this formation of this optic axis. So one of the neat things you can do with a birefringent crystal like calcite is you can send in unpolarized light if it's sent in the right direction, and you can actually get two beams of light that come out of the crystal, and each beam has linearly polarized light, and the polarization axes of the two light beams are perpendicular to one another. So this picture is trying to represent that. In this incident beam, you see that the electric field component could be vertical, right, as you see with the orange arrow, or could be coming in and out of the screen, as you see with these dots. So again, that's representing the fact that unpolarized light coming into the crystal could have a component of electric field that is vertical or in and out of the screen. When the light actually goes through the crystal, there is a separation of the light path into these mutually polarized beams. And what exits then is the so-called ordinary ray and extraordinary ray. And these two beams, again, comprised of linearly polarized light, and the polarization axes are perpendicular. If I see you in person, I'll show you a demonstration of this. It's really cool. And also, this will produce a double image. So and again, I can show you this in person. If I put a piece of calcite down on, let's say, some text, and you look at the text through the crystal, you'll see two images. One formed by the ordinary rays and one by the extraordinary rays. So it's a neat effect. Okay, but you can actually engineer with birefringent crystal. It's not just sort of a neat magic trick. One of the things you can do is, if you get the right thickness and send light in the right direction, and this is going to take some crystal preparation. There's going to have to be some cutting and polishing. But if you do that, you can make a polarization rotator. So if you send in linearly polarized light in this picture, let's say the light is oriented along these incoming orange arrows here, right? So that's the axis of the electric field. This birefringent material can actually rotate the polarization axis through some angle theta. And the amount of rotation you get is going to depend on how thick that material is, the distance the light travels through the material, the wavelength of the light, and the value of the refractive index. Okay, so again, you could engineer and make a polarization rotator. Now you'll notice that, I could get the same output, well, the same behavior if I just use a linear polarizer. So if I just had this linearly polarized light coming in, and I had a single dichroic polarizer rotated so that its axis, its transmission axis, was along the desired output axis, I would get light coming out of the polarizer that had its electric field axis now rotated. The big difference, though, is that linear polarizer is going to reduce the intensity of the output light, because that dichroic polarizer utilizes absorption of light energy. This birefringent polarization rotator, this is transparent to the light. So you're going to have, well, it's going to be a slight amount of absorption naturally, but you're going to have most of the light coming through with its axis rotated. So that's a big advantage. Okay, now let's talk a little bit about scattering of light. This is another optical phenomenon. So scattering of light means that light comes into a bunch of so-called scatterers, and what they'll do is they will scatter the light, they will send the light in random directions. Now, it's really an absorption re-emission process, but the light is sent in different directions, so we call that the scattering of light. Notice this is different than reflection off of a surface. In the surface, right, the atoms and molecules are very close together, forming an actual interface between two solids or two liquids or liquid and a solid. Scattering of light does occur in solids and liquids, but particularly in gases where the atoms and molecules are relatively far apart. Okay. Speaking of scattering in gases, the amount of scattering that is produced, so how much the light changes direction. If you look at the intensity of the light in different directions, if that's many directions, we would say that's a lot of scattering. So the amount of scattering depends on the size of the scatterers compared to the wavelength of the light, if you look at scattering theory. And there are different regimes of scattering. Rayleigh scattering is a common one, and it's an important one. This is where the size of the scatterers is small compared to the wavelength of light. So you encounter this a lot naturally, because if you think about it, visible wavelengths of light are on the order of around 500 nanometers. Atoms and molecules in our atmosphere are on the order of a nanometer, right? A few nanometers, tens of nanometers for bigger scatterers. So that is Rayleigh regime. And in the Rayleigh regime, the amount of scattered light is proportional to 1 over the wavelength of the light to the 4th power. It's a really, really strong dependence on the wavelength. So what that means is that shorter wavelengths are going to scatter much more than longer wavelengths. And again, by when we say scattering more, that means the light is sent in more directions. More of the light, right, is sent in random directions. Okay, so this is the answer to why does our sky appear blue, right? If you look at the scattering of sunlight in our atmosphere by primarily oxygen and nitrogen, we know that on a nice sunny day, right, if you look at a portion of the sky, it appears bluish. And if you look at the sun, which you shouldn't without proper eye protection, but if you looked at the sun or see a photograph of the sun, right, with proper eye protection, it appears sort of yellow-white. But at sunrise, sunset, if you look towards the sun looks more orangey red. Okay, so you can explain this by Rayleigh scattering. I'm trying to do that with my picture here. Now, just realize that this is not drawn to scale at all. What I'm showing here, this green hemisphere represents the Earth. The atmosphere of our Earth is roughly 50 kilometers, right? It gradually just fades away into space, but roughly 50 kilometers. So if the sun is overhead, here, this little triangle represents us. If the sun is directly overhead, the sunlight is traveling through roughly 50 kilometers of atmosphere. Now, in that process of traveling, the violet and blue light is going to scatter much more than the red, orange, yellow. Okay, so the blue and violet light is scattered in all directions, right? It's bouncing all around, getting scattered all around. So when we look at different portions of the sky, we're going to see some of that blue and violet light's going to enter our eyes, and we see the blue-violet. And if we look at the sun, again, you shouldn't without proper eye protection, you're still getting all colors of the sun coming towards you. Even though the violet and blue are scattering, they're traveling through relatively small distance of atmosphere to get to your eye. So you're still getting an appreciable amount of blue and violet light entering your eye along with the red, orange, and yellow. So you sort of see this white light. Okay, now if you contrast that, there's a photo of a nice blue sky with some clouds. I should mention that the clouds, those are larger scatterers, right, that make up the clouds, those particles that make up these cloud formations. So those larger scatterers, in fact, tend to scatter all wavelengths fairly well. So you sort of get this whitish color. Okay, now let's contrast this to, let's say, sunset. So now this is us again right here. Here's the sun. If you look at how much atmosphere the sun has to get through now, right before it's dipping below the horizon there, it's going to be roughly 820 kilometers if you do the math. Okay, now by that time, that's a pretty big distance compared to 50 kilometers. So by the time the sunlight reaches your eye, a lot of that blue, violet, and even green wavelengths have scattered away. All right, so they're not going to be present in this light that's coming directly to you from the sun. So when you look in the direction of the sun, you see that red orangey light. Okay, so there you go. And I think I have a photo. Look at that. Isn't that beautiful? There it is. Okay. Scattering can produce linearly polarized light. It's completely a geometry thing. If you happen to receive some scattered light where the direction of the scattered light coming into your eyes is perpendicular from the incident direction, this will only be polarized light, linearly polarized light. Okay, if you just look at the geometry and remember that the electric field has to be perpendicular to the direction of travel. So that can happen. Okay, absorption of light, another optical process. When we talk about the absorption of light, we mean that the energy is absorbed from the electromagnetic wave by the atom or molecule. It's not scattered. It is absorbed by the molecule. It then goes to a higher atomic state. Okay, now the atom or molecule may lose that energy then in a collision or by re-emitting light. Okay, relatively speaking, a little bit later. But the absorption of energy means energy is absorbed, taken out of the light wave by this atom or molecule. Now, if you look at a certain atom or molecule, there are certain frequencies or wavelengths that are absorbed much better than other frequencies or wavelengths. And that's because of the atomic energy level structure of the atoms and molecules. You may have talked about atomic energy levels or molecular energy levels in chemistry. We'll talk more about them when we get to some quantum optics and atomic physics. Okay, but long story made short, certain frequencies will be absorbed much better than other frequencies. Okay, so you can produce what's called an absorption spectrum for a material And what you do there is you have a whole bunch of wavelengths. If we're talking visible, basically white light passing through the material, and you look to see what comes out, right? And if you don't see a lot of light at a particular frequency coming out, that means it was absorbed, strongly absorbed. So by knowing what frequencies or wavelengths are absorbed, you can produce the so-called absorption spectrum. Okay, so here's a typical absorption spectrum. This actually shows several. And you can see on the vertical axis, it's just a normalized amount of absorption. So the higher the number, the more absorption. And then here's versus wavelength in nanometers. So this is over the entire visible spectrum and a little bit into the infrared. And I chose this one just because we can see something here. This is some chlorophylls and also phycoerythroblin. I'm not sure what that is, but also beta carotene. I just found this. These are some organic materials. Okay. If you look at the chlorophyll absorption spectrum, let's look at, for instance, number 2. Okay, you can see this peak right here. That's a strong absorption in the blue violet. Now there's not a lot of absorption, right, in the green yellow, right? And then there's strong absorption again in the red portion of the spectrum out here. Okay, this would be red out here. So this material is very good at absorbing the short blue violet and then the red. Okay, so imagine you have a plant, right, that has a lot of this chlorophyll. White light hits the plant. A lot of the blue violet and the red is going to be absorbed by the chlorophyll. So what's going to get reflected from that plant? What's left to get reflected? Well, primarily, right, the greens. So that's why, right, this plant is going to look greenish to you with that reflected light. Sunlight hits it, only the greenish frequencies are getting reflected strongly. Okay, you can see that with spectrum 3 also, that type of chlorophyll. And then if you look at beta carotene, that's pretty cool. That's number 5. So that one's a little bit hard to see. That's this one. So if you look, here's number 5. You see that? Okay. Lots of absorption all the way to around 500 nanometers. And then it just drops off. So hardly any absorption beyond that. Well, what wavelengths are beyond that? That's going to be orange and red. So something that has a lot of beta carotene in it, white light hits it, those shorter wavelengths are going to be absorbed. What's going to be reflected is orange and orangey red. And again, I'm not a biologist by any means, nor a botanist, but I know that traditional carrots, right, have a lot of beta carotene, and at least the regular old carrots that we think of are claimed to have a lot of beta carotene. And what color do they look when white light reflects off of them? They look orange. Okay. Now I know there are different types of carrots, different color carrots, and it'd be interesting to know if they have a lot of beta carotene, those different colors. But I know orange carrots do. Okay. And then here's a little quiz. So here's an absorption spectrum I found. So again, it's just a normalized absorbance. So what color, what color do you think this material is? If we hit this material with white light, whatever this object is that has this material, right, made out of this material, what color do you think this is going to appear? Well, let's see. There's lots of absorption with the shorter wavelengths. In fact, it's pretty good absorption all the way out to the reddish wavelengths. So my guess is this will look red in reflected light. And sure enough, this is red garnet. So the absorption spectra of red garnet. Okay, that's it. Just a little bit of bonus material. Hope you enjoyed it, and I'll see you in the next video. Bye-bye.